They usually don't miss it.
Class can go in the opposite way here, so they're probably not going
Well, all right then. We'll see how determined I am to teach them next year then.
Teach them next year.
They're both academy kids still.
Yeah. Hey, are you planning on coming to class today? No. Oh. I see. So like an hour. Yeah. Okay. Okay, sounds good. So,
No go.
if he comes, it'll be quite late. He's got a job he's doing.
Well, all right then. It's been a bit since we met, so let's remind ourselves of the crucial thing we talked about last time. So last time we finished our conversation of regular expressions, and then we moved on to something called the pumping lemma. And the pumping lemma was to prove that a language was not regular. So let's remind ourselves, what is a regular language?
It's a language that meets a certain set of conditions.
It's a language that can be recognized by a DFA. If there exists some DFA that recognizes it, it's regular. If it's regular, there exists some DFA that recognizes it.
A regular expression. Sorry.
Not talking about regular expression,
Right.
but regular language.
Right.
And then we showed that NFAs are logically equivalent to DFAs. Non-deterministic finite automata are logically equivalent to deterministic finite automata. And then we showed that regular expressions are also logically equivalent to. So the languages generated by regular expressions are also regular languages. So for most of chapter 1, all we were talking about regular languages over and over and over again. And then we introduced a way to demonstrate that not all languages are regular. Some languages are not regular languages. There are no regular expressions or DFAs or NFAs that recognize those things. And our typical example was 0 to the n, 1 to the n. That's a language that is not a regular language. You cannot create a regular expression that generates that language, or you cannot create a DFA that recognizes that language, etc. And the way that we proved languages like this were not regular languages was using something called the pumping lemma. And so what we proved is that every regular language has what we call the pumping property. And so if we can prove that something does not have that pumping property, then we prove that that language is not a regular language. If alpha implies beta, not beta implies not alpha. And that's the logic for how we used it. So what was the pumping lemma? What was this pumping property that all regular languages have? So for any regular language in existence, this condition is satisfied, this pumping property. So let's wrap our heads around what the pumping property is one more time. Given any regular language, or maybe a better way to think about it is given some DFA that recognizes some regular language. We'll think about it in terms of the machine. I think that's an easier way to make sense of this. Given some DFA, there exists some number p, we called it the pumping length, some natural number. Typically we use a number of states in the machine, but we could use 10 times the number of states in the machine and that would work too. But typically we think about p as a number of states in the machine. So given, so for any DFA, there exists some number p called the pumping length, such that for any string of at least that length, we can split that string up into x, y, and z. And we think about the y part as the part of the string that's guaranteed to loop. Basically, if my machine only has p states, and I take a string that has length at least p, I'm guaranteed that string is going to loop. That's essentially what the pumping property says. So, given some number p, for any string of length greater than p, there exists a way of splitting up that string. We think about x as a part before the loop, y is the part that loops, z is the part after the loop. There exists some way of splitting up the string into x, y, and z, such that the part up to and including the first loop comes before your pumping length, and the loop has length at least 1. And so when y is the loop, then for any I and n you pick, I could be 10,000, x, y to the 10,000 z should also be in the language. If you take the loop, if you can take the loop once, you can take the loop 1,000 times. And when it's all said and done, you should still end up with a string in the language. So for any length p, given some DFA, then there exists some number p such that for any string of length greater than p, that string can be broken up into components x, y, and z, where x and y are less than or equal to p, and y has length at least 1, such that for any natural number you choose, x, y to that natural number z is still in the language A. So if A is a regular language, we're guaranteed this about it. Or if you have some DFA, we're guaranteed this about it, where A is the language of the DFA.
Why exactly do they call it pumping?
Because you can pump up how many times it goes through the loop, and it's still in the language.
Okay, so that's what.
So that's where the pumping comes from, the idea that you make it take the loop more. You pump up how many times it goes through the loop. Or you can pump down how many times it goes
So
through
the
the loop.
only way for it to get out of the loop is for it to stop being 0 and be 1.
Well, why is it going through the entire loop? Why is a part of the string read going through the entire loop? So if I do y once, that means I went through the entire loop once. Now I'm back to where I started. So I can do y again. And I can do y again. I can do y as many times as I want before I continue with the z part, which ultimately gets me to an accept state.
Which can only happen if another character was introduced, essentially, into the string.
Right, y has to be at least one character. The loop could possibly read 10 characters to get through the whole loop, but the loop has to have at least one character. Because the smallest loop I could have, if that's my state, the smallest loop I could have is just going back to the state like that.
I was just
Reading a
saying-
0 or a 1.
Yeah, I was just saying that it had to be a 1 or a 0. If it was a set of zeros, it had to be 1 to get out of the loop. Or it had to be, if it was a set of 1s, it had to be a 0 to get out of the loop.
Well, this has nothing to do necessarily with just binary strings.
Okay.
We could be talking about any language. We could be talking about some machine recognizing words in the English language somehow.
Right.
So it has nothing to do necessarily with zeros or ones. We just like to use those symbols.
Yeah, what I'm saying is that the character has to change for it to get out of the loop. Right? Understand?
I mean,
Like the pattern has to change.
sure, but whether it does or doesn't is irrelevant to the pumping property.
Okay.
All the pumping property cares about is it had to go on a loop somewhere, and so it can go on that loop again.
Can Z be the empty string?
Yes. Because you can pick a string of exactly length p, and the xy can completely use the p.
So what about DFAs that don't have a loop in them?
DFAs that don't have a loop in them. So given some DFA that has 4 states, if it does not have a loop, the longest string it can accept is length 3. So given that DFA, I could say for any, there exists a number, I'll call it 57, such that any string of length 57, this is true. It's vacuously true now for that machine, for that DFA. And so DFAs that have loops are going to be able to accept strings of infinite length. And so you can pick some number. There is some number. Has to be more than the number of states where we're guaranteed there's a loop.
Right.
So we typically pick p to be the number of states, but that's just helps us think about it, work with it. P could be 10 times the number of states, and it still works. Make sense? And so the way that we actually use a pumping lemma is we negate this thing. So if we call this right here the pumping property, then here's a negation of the pumping property. So when we show that a language is not regular, we show that for any p you choose, I can find some string, length greater than p, such that no matter how you break up that string, as long as you keep the xy part less than or equal to p and the y part greater than 0, I can always find some number of times to run through the loop, such that running through the loop that number of times gives you something not in the language. Right? And we talk through examples of this all the time. We won't re-go over all the proofs. If you want to see a full proof of this, you can watch last time's lecture. But we'll remind ourselves of just speaking verbally about how we might prove that something like this is not regular. the way we think about it is a proof by contradiction. Someone comes in and they say, I have a machine, I have a DFA that recognizes this thing. So I ask them first, okay, how many states are in your DFA? They give me some number, it doesn't matter what number they give me, they'll give me some number like 20 states. So I say, okay, now consider the string 0 to the 20, 1 to the 20. So notice that they're giving me any p that they want. Any length that they want, we're pretending they give me 20. But they could give me anything. So for any p they give me, I now choose a string that has length greater than p, such that now I need to show them no matter how they divide it up, as long as they satisfy these two conditions, I can find a way of pumping it such that we get something not in the language. So I say, okay, you give me any number p you want, here you go. Now here's a string of length greater than p. Now, since x, y has to be less than or equal to p, wherever the loop is y has to be completely in the zeros. Right? If I make this string 0 to the 20, 1 to the 20 equal to x, y, z, so I break this up into a substring x, y, and z, and if the x, y part, if the length of this portion of the string is less than or equal to 20, then x and y are completely contained in the zeros. Right? So then, x, y twice z then is going to be something that has more zeros than ones. And so this is not going to be in A. If A was equal to the set of all these strings where n is a natural number. So this is not a regular language because it can't be pumped. We found a string that can't be pumped. If it's a regular language, every string of sufficient length can be pumped, as long as it can be divided this way. We found one that couldn't. Therefore, this language is not regular. Make sense? So that's the pumping property. We got to stress that because, or the pumping lemma, we got to stress it because as we get into chapter 2, we're going to get a more complicated version of the pumping lemma for context-free grammars, proving that grammars are not context-free. So good to have that in mind. Okay, so that's a good recap of last time. So now we're going to jump this time to start talking about grammars, in particularly regular grammars. And pretty much the rest of the stuff we're talking about today, it's not going to be in the book. The book skips over talking about regular grammars, which I think is a mistake. So at the end of the pumping lemma here, we finished chapter 1 according to the book. And the rest of this is add-on, and I'll tell you when we start chapter 2. We start chapter 2 at the whiteboard. Okay, so the author skips over talking about something called regular grammars, but we're going to introduce it because regular grammars, it turns out, are going to be logically equivalent to NFAs and DFAs and regular expressions as well. So let's just start with an example before we try to nail down what exactly grammar is, or regular grammar is. So here's an example of a grammar. And you'll notice that we have capital letters and then lowercase letters. We call the capital letters variables. We call the other letters or symbols terminals. We can replace the variable here with that or with that. We can replace this variable with that or with that. We can replace this variable with that or with that. You keep doing replacements until all your variables are gone. Once all your variables are gone and all you're left with are terminals, then we say that's a string generated by the grammar. And you always start out with the variable that's listed in the top left corner. So let's generate a string with this grammar really quick. So starting out with s, we always start with s. Now I can take my s and I can either replace it with this or with this. You with me? So I'm going to take my s, I'm going to replace it with this, why not? So I take my s and now I replace it with A, capital A, B.
So what are those things you replace your terminals?
The characters?
Like our terminal? Yeah, are they the same thing?
Terminal, variable, terminal.
So there's variables inside of the terminals.
No. Little a is a terminal.
Oh.
Big A is a variable, little b is a terminal.
Variables inside of variables then. So that A is a variable inside of S.
All my capital letters here are called variables.
Right.
The rest are called terminals.
So
We are going to keep replacing variables following these rules here. These are rules for how we can replace our variables until there are no variables left. When there's no variables left in the thing we're generating, and there's just terminals, then we call that a string generated by the grammar. So far this is not a string generated by the grammar because it still has a variable in there.
So are your terminals, symbols in an alphabet?
Yeah, like letters.
We'll get to that, but yes, ultimately that's what it's going to be. We just call them terminals, we don't call it the alphabet, but we'll use the same symbol for our terminals that we use for an alphabet because we basically think about it the same way. Okay, so I can take S and I can replace it with little a, big A, little b. Okay, so now I have an A in there that I want to replace. I can replace that with little a, big A, or just a little a. I'll replace it with a little a, big A. So we have A, then what I replace this with, which is little a, big A, and then we have that B.
Oh.
So because it repeats itself, would you ever just want to put a repeater symbol on it, or whatever it's called?
No, we don't use regular expression symbols here.
But it's infinite.
It could
Well, maybe. If this couldn't ever terminate, then it would never generate a string. So then I could also replace that big A with little a by itself if I want. So now I can do A, I can replace that big A with just little a, B. Now notice that this has no variables in it. So that right there is a string generated by the grammar. So the grammar can generate the string B. Let's do another one. You always have to start with S. We can also have replaced S with little b, big B, little a. So little b, big B, little a. B can only go to B or the empty string. We'll do the empty string, and we're done. So it can also generate the string BA. Make sense? And obviously there's an infinite number of strings that we could generate with this grammar. And so there's an example of just a random grammar. This is not a regular grammar, this is just a random grammar I'm showing you. We'll define a regular grammar later. Regular grammars are going to be logically equivalent to DFAs. And so in introducing a regular grammar for you, I'm going to create the regular grammar that does the same thing as this DFA here. So here's a DFA. This is the accept state. I'm calling the start state S, and then this other state over here, A. One it goes over there, one it goes back. And so obviously it's accepting strings that have an odd number of ones. Right?
Okay.
Odd number of ones, even. Odd, even. Okay, so now we're going to create a grammar that recognizes, that generates the same strings that this machine recognizes. And how do we do that? We start with whatever our start state's called, S. And we say that that can go to, sorry, let me make sure I get the order here right. Between symbol and then variable. Where did I write this out? Oh, we're back here. Regular ones. Okay, terminal then variable. Alright, so we can do a 1 and move to A. From S, we can do a 0 and move to S. From A, we could do a 1 and move to S. And from A, we could do a 0 and move to A.
Okay.
Right? And now, so if we were to look at a string that this will accept the string 0, 1, 1, 1, 0. This machine will. Let's look at how this generates it. So we start with S, then 0 goes, we can replace S with 0S, which is logically equivalent to, we read a 0 and we're back at S. And now, I use this rule, right? Here's my rules for my grammar.
Isn't that S goes to 1A or 0S?
Oh yeah, I just put them on separate lines. So this is yeah, we could consolidate this and we could have rewritten this as a grammar. S has the option of going to 1A or to 0S, and A has the option of going to 1S or 0A.
And there can be as many of those ors as you want. Is that right?
Yeah, because an or here is just like just doing another line. So this is shorthand actually for doing this. Okay, so there's our grammar that we said. So we're starting out with S, and we're trying to generate this string, 0, 1, 1, 1, 0. So we start with, first we're going to use S goes to 0S, so S goes to 0S. Then we're going to take that S and we're going to replace it with 1A. So that goes to 0, 1A. Then we're going to take that A and replace it with 1S. So we have 0, 1, 1S. Then we're going to take that S and replace it with a 1A. So we're going to get 0, 1, 1, 1A. And then we're going to take that A and replace it with a 0. And so now we get 0, 1, 1, 1, 0A. And you'll notice a problem with our grammar so far.
It doesn't terminate.
It never terminates. So we're missing one more thing. We want it to be able to end whenever it's in this state.
Can you use an epsilon transition?
We can use an epsilon transition. So A can also just, if you're in the A state, we say you can just bell out if you want.
Because it's the
Except
except state. Okay.
Perfect. So now this goes 0, 1, 1, 1, 0. And you'll notice that this was basically just saying, keeping track of the states that we were in. So we start out in S. When we read a 0, we're back in S. Then when we read a 1, we're over here in A. Then when we read another one, we were back here in S. Then when we read another one, we were back here in A. Then when we read a 0, we were back here in A. Then we terminated.
You could have terminated any time.
Anytime we were in A, we could have terminated, and it would have accepted. Notice only A goes to epsilon, not S. So hopefully, I'm not going to prove to you that DFAs can be converted to linear grammars, and linear grammars can be converted to DFAs. I'm just going to give you examples and help you get the intuition for it, since the author skips over it altogether. I didn't want to spend too much time on it. So hopefully this gives you intuition, makes you feel like, yes, if I gave you the DFA, you can come up with the grammar that generates the same strings as the DFA recognizes.
That is a regular grammar?
This right here is a regular grammar, the one I've drawn here.
And above it is not a regular grammar.
Above it was just a grammar. This is a regular grammar. We'll go over right now exactly the definition of what we call a right linear grammar, and then I'll tell you what a left linear grammar is. I could have just looked at that for my symbols.
Are you going to tell
Then
us
you go look at my notebook.
what a grammar is in general? No?
In short, a grammar is just a set of rules like this, but you can have strings of variables over here and strings of variables and terminals over here. So I didn't just have to have one S goes to this. I could have had SAS goes to that.
Oh.
So
And that would have been what we call a context-sensitive grammar. And that's clear up with Turing machines. So we'll get there. But for now, we're going to talk about pretty much the simplest grammar we can.
Okay.
So this grammar is called a right linear grammar. And let's get its exact definition. A right linear grammar, G, is a four-tuple, G equal to V sigma R S, where V is a finite set of variables. For this grammar over here, that would have been the set containing S and A. Sigma is a finite set of terminals. For this over here, that would have been 1, 0, and epsilon. Important, sigma intersect your variables better be empty. Something cannot be both a variable and a terminal. As a matter of notation, we use capital letters for variables to make it obvious when you're looking at it, which is which.
Is the empty string always
That will never be used as a variable.
what I'm saying? Is it always a terminal?
No. I can have the grammar. We could have gotten rid of that.
Okay. But But then, does that?
Yeah, it still terminates because you can get rid of your b, which is lowercase b, and your a, which is lowercase a. So you can rewrite your s in terms of a's and b's. So everything ultimately terminates.
Okay.
But even if everything didn't ultimately terminate, so let's say I gave you the grammar like this. With me?
Okay.
That's perfectly valid grammar. What are all the strings it generates? None,
Oh, okay.
because none of them terminate. So the language of that grammar is the empty language. Okay, back to what a right linear grammar is. So we have a finite set of variables, we have a finite set of terminals. Those cannot have anything in common. And then R is a finite set of rules. We typically just write the rules when we're talking about a grammar. The same way that we typically just draw a picture like this when we're talking about DFA and we don't bother writing out all the other sets as inferred. Similar thing here. R is typically just what we write out, the rules. But R is a finite set of the rules of the form. We have three options. We can have variable goes to terminal variable, or we can have variable goes to terminal, or we can have variable goes to the empty string, where A and B are variables, and A is in our set of terminals. And then finally 4, this S right here signifies what our start variable is. We typically use an S for the start variable, but there's no reason that you have to. So that's what we call a right linear grammar, and it is a regular grammar. A left linear grammar is also a linear grammar, and that's just when you switch the order on those two.
Okay.
So we chose to use a right linear grammar as opposed to a left linear grammar. They're logically equivalent. Both of them are regular grammars.
Is there a type of grammar? Why isn't there just a type of grammar that's left or right?
So the terminals will start being produced on the right side rather than left.
Yeah, which way it generates.
Yeah.
Yes. Exactly. So this is always generating on the right end of the string. If we did a left linear grammar, it would always be generating on the left end of the string. And generating on the right end is more natural. This one right here was a right linear grammar. Notice that our variable was always on the right end of the string. With a left linear grammar, your variable will always be on the left end of the string, and you'll generate the string from right to left. It's more natural to do it from left to right. So when we use a regular grammar, we typically choose a right linear grammar over a left linear grammar.
So a right linear
But
grammar,
that's just because we are more comfortable with
it
it.
has to have the variable on the right side.
The variable will always be on the right side.
It can't be in the middle, it can't be on.
Yeah, there's no way for it to get there.
Okay,
Then
All the rules have to be one of these three forms. Well, either it's on the right side or the variable's gone altogether.
but there are grammars that can have both.
Yeah, this is just a right linear grammar.
Yeah, that regular
And it's like
grammar has
as simple a grammar as we can talk about. As not as simple, but as nice. It works very nicely, very naturally. You're always just replacing the rightmost variable with the next symbol. It's real easy to read about, real easy to think about. Yeah, because it's logically equivalent to DFAs. And those are real easy to think about. Okay. So now, some terminology about grammars in general. For all grammars, this terminology holds. With me?
Okay.
All right. If U, V, and W are strings of terminals and variables, some combination of terminals and variables, and we have the rule, some variable goes to some string of terminals and variables, some rule, something like this. Here's an example of one.
Okay.
Or it could have been a rule like A goes to B, that was supposed to be a capital C, lowercase c, D. So A goes to, not equals. So here's A, and here's some string of terminals and variables. Here's some rule, right? So if U, V, and W are strings of terminals and variables, and we have the rule A goes to W as a rule, we say that U, A, V yields U, W, V. In other words, we can take the A and we can replace it with W. You already know that you can do that. If you have the rule A goes to W, then you can take your A here and replace it with W. Terminology for that is UAV yields UWV. if you can replace the A with the W using one rule. And we write an arrow to it. UAV yields UWV. And I've already been using that when we were doing these. It's very natural notation. With me? So I would say this yields this yields this yields this, etc.
So really that's part of your definition of a grammar, right? Because your rules are defined in terms of what variable yields what string.
Your rules state what terminals and variables are yielded from one variable, but we are saying that this whole string yields this whole string. So it's not just talking about the rule. Good, there's a little bit of subtlety there.
So is that really a complete definition?
This is a complete definition. This has nothing to do with the
Because
definition.
we don't.
This is just terminology that we're going to use.
I mean, I understand what it's saying. I'm just wondering if there's a formal way to state your arrows. Are your arrows like a function, or are they like what are they?
You're saying, so the way I'm using the arrows here and the way I'm using the arrows here aren't quite the same.
Right. What I'm saying is, in your definition,
In our definition
we
up
have a
here,
sense of what your arrows are, but like, are they formally defined somewhere?
oh, we're not defining them using set theory or functional notation or anything like that.
That's what I was wondering.
Right? So it's just implied, well, first off, this is a set of these themes. So anytime you see the rules listed out here, R is actually a set of those things. And this whole symbol, you can treat it all as like one symbol, and it means something.
R seems like it's pretty much the transition function, the delta.
Right, it acts a lot like the delta function. And you'll notice that when we did that here was R, and if we roll out our delta function here, which is all the transition arrows,
It's the
they
same.
almost say the exact same thing. Right, they
So
say logically equivalent things.
Is R actually a set, like a function?
R is a set of these production rules. Here's a production rule.
And the production rule can be written as a list.
The production rule can be written as a variable, arrow, a terminal, and a variable. So that symbol and that symbol have to be in that set. That symbol has to be in that set. And this is, R is a set. So if we were to write R is equal to the set, this thing, comma, this thing, comma, this thing. And all together, it's one piece of notation.
So we just don't define the arrow.
It's just a piece of notation now. It doesn't mean implies or anything like that. It's just a piece of notation. We're saying when you see this arrow symbol in this context, it's always going to come up with this form surrounding it.
Okay.
And here's what you can do with the arrow.
I now start to understand the syntax of old languages. They use arrows and stuff to set variables and things like that. Just like this.
Oh, you're saying programming languages?
Really old ones, they instead of using equal sign, they actually use the arrow. Not old, just machine, like really fundamental, fundamental programming languages.
Been working hard?
Hardly working.
Well, all right then. You missed a lot.
Did you do a recap?
Yeah, I can. I'll do a special one for you sometime tomorrow.
Sounds good.
Not sure when I'll get uploaded. But I'll go over it all word for word.
Really what my question is there a set theory definition of an arrow that exists?
There is a more primitive definition for what we mean by this arrow.
There's not.
No.
Okay. Okay.
Sure, you could define it as like some sort of function, but just gets messy. We have to get intuition for what it means.
Yeah.
Okay, so we went over what it means for one string to yield another. UAV yields UWV if we have the rule A goes to W in our grammar. So that's what it means to yield. Now, we say that U derives V. To give you a sense of U derives V, here's an example. OS, or 0S here, derived 0, 1, 1, 1, 0. Because with a bunch of yields, we could ultimately get to that string. If we can get from here to here, maybe don't think all the way to the end and think it has to be an end one. Since we could get from here to here, then this derives this. That's what we're going to say. So we say that U derives V, written U arrow V with a star above it, since we're doing a bunch of yields some amount of times, so the star makes good sense there. Provided that there exists some sequence of strings of terminals or variables where n is greater than or equal to 0, such that U yields U naught, yields U1, yields U2, dot, 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 yields UN, ultimately yields V. Or if U is actually equal to V, then we also say U derives V. So every string derives itself. Okay, so that's what we mean by yields. That's what we mean by derives. And so finally, what's the language of a grammar? It's a set of all the strings of terminals you can get where that string is ultimately derived from the start symbol.
What is sigma star? Is that a different?
Sigma is a set of terminals. Sigma star is any string of terminals you can get. So this is any string of terminals you can get where the string is ultimately derived by our start symbol. Okay, now for the rest of you who just got in here, let's give you a sense of what we're doing with these grammars really quick, and then you'll have to go and get up to date on these definitions yourself, but I think just seeing the grammars in action will be enough to help you keep up with what we're doing from here on out. So, we're talking about grammars. Grammars are a set of rules like what I have right here. All the capital letters here we call variables. Everything that's not a capital letter we call terminal. Now, what these arrows are saying is, if I have an S, I can replace it with A, B, I can replace it with this, or I can replace it with this. Any capital A I have can be replaced with this or this. Any capital B I have can be replaced with this. This will ultimately generate strings of things that aren't variables, things that don't have any capital letters in it. So let's give you an example. So we always start with the top left variable. In this case, that's S. Now, what can I replace S with?
Little a, capital A, little b.
Or I could have done that one.
Or that.
We'll do this one. So I can replace that with little a, little b. Okay, what can I replace capital A with?
Little a, big A.
Little a, big A. So now it's A, replacing capital A, we have A, capital A-B. All right, now I can replace that capital A again. What should I replace it with?
I'm not understanding your leap from little a, big A, little b.
Here I have a capital A.
Oh, yeah.
So I'm replacing that capital A
Yeah.
with little a, capital A. I can always replace my capital A's with a little a followed by a capital A.
Okay, yeah.
Follow that?
Yep.
And once again, I still have a capital A in there, so I can replace that. What should I replace it with?
A little a.
A little a. So now I have A, B. Notice that this does not have any variables in it now.
Yep.
Since it doesn't have any variables in it, we say that we're done, and this is a string generated by this grammar. The set of all strings generated by the grammar is the language of the grammar. Good? Now, we were showing that these grammars, we can create grammars called right linear grammars, which are, oh my, wow. Crazy. My shoe just came off. All right. So here's some DFA, which recognizes strings that have an odd number of ones in them. Right?
Yeah.
And we call this state S, and we call this state A. We're going to come up now with a grammar that does the same thing as a state machine, as this DFA.
Okay.
So our grammar, we start it with an S. same as the start state. And we say that on a 1, we then have an A. So we can replace S with a 1A, or we can replace S with on a 0, it goes back to S. 0S. And an A can be replaced with on a 0 we can go back to A, or on a 1 we can go to S. So 1 takes us back to S, 0 takes us back to A, right?
Yep.
So now, let's start generating some string with this. So we start with S. S, what should we replace it with?
1A.
1A. So notice that's the same thing as we start in state S, we read a 1, now we're over here in state A. Logically equivalent. Now what should we replace the A with?
1S.
1S. So now we have 1S. And that's the same thing as we were in A, read a 1, go back to S. Now what should we do?
OS.
0S. So now we got 110S. Now what? Maybe read another 1. So now we got 1101A, right? How are we ever going to get rid of our variable? So the last thing we need to do is we need to say when we're in state A, we can also just replace our A with the empty string. And so finally replace A with the empty string and we get 1101. So there was a string generated by this grammar. And notice that it was also a string recognized by this machine. When we read a 1, we go to here. When we read another 1, we go to here. When we read a 0, we go to here. When we read a 1, we go to here. We're done. So we just created a grammar that was logically equivalent to a DFA.
So
Now our grammar had to follow 3 rules here. Our grammar had to be of the form, a variable goes to a terminal followed by a variable, or our variable goes to just a terminal, or our variable goes to an empty string.
So it can't go to just a variable.
So it can go to just a variable. In this machine, we happen not to use that, but it can go to just a variable.
Just a variable or just a terminal?
Or just a terminal, sorry.
Okay,
Not just a variable, sorry. Don't let me use the wrong language. So yeah, A can go just to a terminal, A can go to the empty string, or A can go to a terminal variable.
But it can't go straight to a variable. A variable can't go to a variable.
Yeah, we don't just have a variable goes to a variable. That would be pretty redundant.
Yeah. Right. I just want to, for
Yeah.
sure it can.
You could in a regular grammar. Yeah, or you could in just a random grammar. This is a special type of grammar. A right linear grammar follows these 3 rules.
Okay.
So here, we did not have a right linear grammar with this one. This one is not a right linear grammar. This was just some random grammar. Here we had a right linear grammar. These right linear grammars are going to be logically equivalent to DFAs. Here's just some random grammar to get you used to grammars. Here's the types of grammars that are going to be logically equivalent to DFAs. And so hopefully you see now how if I give you a random DFA, you could come up with the grammar that generates the same strings that the DFA recognizes.
So every grammar can make a DFA, and every DFA can make a grammar.
Every right linear grammar is logically equivalent to a DFA.
Can every grammar create an NFA?
No, because a DFA and an NFA are logically equivalent.
Okay.
Make sense?
Yeah.
And here's another example of why no. You might remember from last time, we showed that 0 to the n, 1 to the n is not a regular language. The set of all strings equal to that. 0 to the n, 1 to the n, where n is a natural number. We used a pumping lemma last time to show that this is not a regular language. There is no DFA, there is no NFA, there is no regular expression where this is the language. Let's come up with a grammar that has that as a language. That's real easy. I'll have A goes to, I can have it go to 0, A1, or the empty string.
Okay.
You see that? So if we wanted to generate the string 0, 0, 0, 1, 1, 1, that's logically equivalent to A goes to 0, A1, goes to 0, 0, A1, 1,
Oh yeah.
goes to 0, 0, 0, A1, 1, 1, goes to finally use the epsilon transition, 0, 0, 0, 1, 1, 1. And so with this grammar, we can easily generate this language, which no DFA could do.
Yeah.
So here already gives you a grammar somehow more powerful than DFA. But if we restrict ourselves to grammars like this, then we're the same as DFAs still.
So it is right that every NFA or DFA can construct a grammar.
Can construct this type of grammar, a right linear grammar,
Okay.
not grammars in general. Okay. And then this is just some terminology about grammars that you'll just have to figure out as we go. And now let's play around with this for a second. So now I want you guys to try and think up a grammar that generates all the binary strings with the substring 1, 1. So we'll make our first rule S. What should S go to?
1s.
A 1S
Or something else.
or something else?
Or an empty.
Or an empty?
No.
An empty definitely isn't going to have the substring 1, 1. So we don't want S goes to empty.
Not yet.
Goes to
One
can't.
Yeah, 1A.
Goes to
1, 1,
1, 1A. Try and generate a right linear grammar that does it.
Yeah.
So you only get to do one terminal at a time.
I'm confused. It's just 2 1s, right?
It contains a substring 1, 1. So here's an example of a string we want to generate. It should be able to generate this.
It should be.
Because
so
it has a substring 1, 1.
Is A the except?
Then you're not going to want to go 1s. You're going to want to go 0s and then 1a.
Okay. So we want S goes to 0S, or it goes to 1A. Okay, what does A go to?
0a or 1a.
0A or 1A.
Shouldn't it go back to 0S?
Oh, not 1a. 1a.
Shouldn't it go back to 0S?
No. Well,
No?
Maybe. 1 sec.
Maybe?
I gotta think about
I
it.
think so, because then you'd be restarting trying to count
Yeah.
the 2 ones. And I think we'd go to 1B instead. So
1B?
Yeah. Yep.
And what should B go to?
Should either accept or
So,
go to
yeah,
itself.
so
So B or the empty string?
You can't do variables.
You can't go to a variable.
Ah.
so
So what do you mean itself?
Well, if it gets
1B?
0b or 1b.
and an empty string.
1B or what?
0S.
Or 0S?
Zero.
Oh, sorry.
No,
No,
0B.
0B?
Or empty.
Or empty.
Or empty?
Yep.
There we go. You got it.
I had to visualize the machine first.
Right. And you probably would have noticed it would have been a lot easier to think about this in terms of a DFA really quick. Right? We could have really quick made a DFA, call this S, here's our start state. Call this one A, which is we've seen 1, 1. Call this B, which is we've seen both ones.
Right.
So here we got a 1, here we got a 1. 0 takes us back here. On an A, if we got 0, I'll go restart because you need 1, 1.
Yeah.
Once we got our 1, 1, we're good, and we can stay here, 0, 1, and this is our accept state. So if you take this, you turn it into grammar, you'd get that exact same thing. It's also useful, maybe the way some of you were thinking about it, is to give some sort of meaning to what these variables are, kind of the same way we give meaning to these states. You think about A as a variable, I've seen at least 1, 1 so far, B as the variable, I've seen both my 1s.
Yeah.
And S is I haven't seen any of them yet. And so giving them some sort of meaning like that also helps us think about it. Right? Okay, so now let's try it the other way. Maybe we'll stick to just 3 variables here. I want you to give me random grammar here, and then we'll come up with the machine equivalent of the grammar. So rather than going from a grammar to a machine, or from a machine to a grammar, why don't you do an example going from a grammar to a machine?
Do you want to write linear grammar?
Yeah, right linear grammar. Give me
1a.
1A. Anything else?
0B.
Or 0B? Good? Where's where we have A go to?
0a.
Anything else?
1s.
1S?
Yeah.
Okay. Where's we have B go to?
0B.
That's it?
Sure. And then epsilon. Epsilon has to be somewhere.
Doesn't have to be.
Epsilon doesn't have to be somewhere,
Does that accept
But
state?
that won't accept any strings.
but it just won't accept any strings.
Yeah.
Because the grammar doesn't generate any strings, because you can't get rid of your variables.
Yeah.
So if you make so your grammar can't get rid of any variables, then your machine won't accept anything.
Then
So you want an epsilon in here?
for it to be equivalent to DFA, it doesn't have to have an epsilon because a DFA must have an accept state, right?
No.
Oh,
This is
we
a
have
valid
to-
DFA.
That's right, that's right.
An empty string.
I remember now. It's the set of accept states which I'm using.
Yep. So you want an epsilon here?
Yeah, I have to be.
All right. So now let's create the machine that does the same. So our machine can have three states. We have an S, we have an A, we have a B. Since B can terminate, we make B an accept state.
You know what we didn't have?
S is our start state.
We
Huh?
didn't have one without a variable.
We don't.
Yeah, we could have just gone to terminal. If we did just do a terminal, then we would have had to write an NFA rather than a DFA, but it still works.
How do you know S is the start?
We always start with the top left variable.
That's right. You can make it an NFA by doing more than one symbol goes to the same variable, right? More than one, so 0.
Oh yes,
one,
and that would have also given us an NFA, and we know every NFA can be converted to DFA.
Okay.
So since you gave it to me like this, turns out I can just draw the DFA directly rather than having to draw an NFA.
So, nice
If
and
you would have,
simple.
maybe, I don't know if you
Should we do it just
broke
for
it or
fun?
not.
Don't we need to have B go to something on 1 for it to be a
Yeah.
DFA? We don't
Oh,
have to
right, so we're gonna have to either draw an NFA here or explicitly draw what we call our reject state.
Yeah.
So let's just start drawing it out. So S on a 1 goes to A, on a 1, on a 0 goes to B, A on a 0 goes to A, on a 1 goes to S, B on a 0 goes to B,
And epsilon just goes to itself.
and the epsilon, which makes it like that. So here so far we just have an NFA. If we want to make it a DFA, then we need to explicitly write our reject state. Our reject state always goes to itself on a 0, 1, and then let's see what are we missing. S has a 1 and a 0, A has a 1 and a 0, B on a 1. Right?
Mm-hmm.
And so there's our DFA.
Just accepts zeros. Right?
It just accepts.
It's a very complicated way of doing it.
Yeah. Not just zeros, right? Because you can get ones.
Oh, that's
As long as there's two.
So
ones.
you can have an even number of ones
Yeah.
and at least 1 0 at the end. Is what it accepts.
But if it gets to B and it hits a 1.
Oh, yeah, we have to order 1. Yeah. We're not going to get this in words very nicely what exactly this thing is. But the point is, if I gave you a right linear grammar, you could come up with the DFA, or at least the NFA, that recognizes the same thing as a grammar. Now, again, the author doesn't go over any of this, which is why we're just doing it fast, and we're not going to do any formal proofs of any of this. You're just going to take my word for it. So, what have we shown so far now? We've shown that linear grammars are logically equivalent to regular expressions, are logically equivalent to NFAs, are logically equivalent to DFAs. And they're all logically equivalent ways of talking about the same languages. They solve the same problems.
Your camera isn't.
Son of a... I even put the squiggly line.
Yeah.
My shoe is driving me nuts. I wonder if there's tape in here. That works. Let's try and get clever.
So,
Let's not flip around.
is it really useful to know that all those are the same thing? Like we just found 4 different ways to do the same thing.
We just found 4 different ways that they're all logically equivalent, solve the same problems. Sure.
Such as all math.
Huh?
Such as all math.
Just all math, yeah. You're still not used to how we think about it's something that you're not going to get used to until we get to Turing machines. That's where the meat of the class all happens. But somehow recognizing languages and solving problems are one and the same things.
Okay.
And so these are all 4 logically equivalent ways of talking about and solving the exact same types of problems.
Just to be clear, when you say linear grammar, are you referring to specifically right linear grammar?
Right or left, they're both linear grammars.
So,
They're logically equivalent.
okay, so left linear grammar would also work.
Yes.
Okay.
Are they the
We just
only
chose
types
to
of
do it
linear
right.
grammars?
Huh?
Are they the only types of linear grammars?
The only types of linear grammars?
Right.
Right and left? Yeah. Well, I don't know. You could probably come up with an up linear grammar and a down one. I don't know.
What's the difference between the linear grammars?
What's the difference? Just the order that you write these in. So this is a left linear grammar,
Right, that's a good, yeah, right.
or a right linear grammar. The variable's always on the right. Left is just swap the order of those. And so if you just swap the orders of everything, now it's a left linear grammar. Does logically equivalently the same. Logically equivalently the same. Logically equivalent. Sounds weird. I don't like saying that.
Terminals.
They're logically equivalent.
Down on the left.
What I was wondering
They
is,
just generate the strings the other way.
is there some sense of a linear grammar that isn't just left or right?
I don't know. Maybe. I know that there's right and left. Maybe the Chinese like writing up, so they have an up version of it, and the down one. Okay.
I feel like it would be linear after introducing 2 dimensions.
Huh? Linear is generating in one direction.
Maybe you can move up and
Yeah,
right.
left, right,
You
up,
can't
and
go
down.
up in a
Well,
dimension.
why are you limiting yourself to 2 dimensions here?
'Cause it's still linear.
I can have a line in 3 dimensions. A line is linear. It just means it's going in a line. Is it going left? Is it going right? Going up? Is it going down? I don't know.
It's not going.
All right. So now some worthwhile things. Couple sum up notes of things that we've been talking about so far. Well, some questions that we can answer about these is probably a fair way to say it. So when it comes to what we've been talking about so far, finite state machines, DFAs, NFAs, regular expressions, linear grammars, all 4 of those things. What are some decidable questions that we can answer about these things? Now, what do we mean by a decidable question? We mean a yes-no question. What are questions that we can answer yes or no to? Right? And that might seem kind of trivial to you. You might think, well, just about any yes-no question you ask, you can give an answer to, right? That seems perfectly natural. And that turns out to be the case with DFAs. So with DFAs, you can ask a question like, does a DFA accept a particular string W? We can determine yes or no to that question every time. If I give you a DFA and I give you a string W, you can always and forever determine yes or no, does that machine accept that string? Right? It's called the membership question. With a DFA, the fact that I even said to you, you think, what a dumb thing to even ask. By the time we get to Turing machines, we can't answer this question. It becomes undecidable.
You can't tell if it will accept the string.
Correct.
Okay.
So,
without running it.
these things that seem, even running it, and so we'll get used to that. So we're going to see that all these questions, which are so trivial, so obvious, so dumb to even ask about DFAs, almost any question you ask about them is decidable. You can answer yes or no to it. By the time we get to Turing machines, we're going to find out that anything that's non-trivial about Turing machines, you can't answer yes or no to.
Is this
And
trig
we'll prove it.
machines?
Huh?
Is this trig machines you're saying?
Turing.
Turret?
Turing.
Alan Turing. Turing machine.
Okay.
Turing machine. You don't know Alan Turing?
No.
Have you seen The Imitation Game? Codebreakers?
You have schizophrenia?
No? Oh, you're thinking of A Beautiful Mind.
Oh.
I think. Russell Crowe.
Yeah, what were you looking to
Imitation Game.
Benedict
About-
Cumberbatch.
Alan Turing.
say? Oh, yeah. The
Code-breaking Enigma.
broke ending.
The
World War II.
German.
That's
Well,
what I call it.
you boys need to get together and go watch it. It's a solid movie.
It's a good movie, yeah.
Has a guy from the Sherlock Holmes TV series.
Benedict Cumberbatch.
I don't know names.
Yeah.
Just some guy. Anyways, so does a DFA accept a particular string? We can determine the answer to that question, yes or no. Right? Let's look at another question that we might be interested in when it comes to machines in general. Are 2 DFAs equivalent? Do they accept the exact same strings? Is that something we can determine yes or no to?
Yeah.
This one, yes, but we have to note something that we didn't prove in this class. They prove it in some classes, but it's a huge tangent to do. So, the author of this book doesn't bother doing it, but some authors do. So, something that we didn't prove is that every DFA has a unique minimum DFA. You can minimize DFAs to the smallest possible DFA that still recognizes the same language. We didn't prove that, but that's something that you can do. Okay, so using that knowledge, we'll show how you can show that two DFAs are equivalent. They have the same language.
Did they have the same unique minimum?
Well, that could be a little bit tricky still if they have the same minimum, because you need to, it doesn't necessarily preserve the labeling. In one machine, I might have labeled the states A, B, C, and D. In another machine, I might have labeled the states 1, 2, 3, and 4. So even when you get them to their unique minimums, they might not match up, because you didn't start out with the exact same machine. But if you and I start out with the exact same machine, and we both minimize it, we'll end up with the exact same minimum, is what we mean by that.
That's what
Right. So
it's
now,
basically the same. I mean,
basically the same.
okay.
So far they're basically the same. The labeling might have just matched up different. But if you and I start with the same machine and we both minimize it, we'll end up with the same machine. Now we got two machines that maybe are logically equivalent. When you minimize them, they won't necessarily be the same thing. There will be a way of relabeling them to check to see if they're the same thing. And if you're already good with that logic, then that's good enough for this. But we can, without having to think about relabeling, we can talk about it in a more rigorous way, how you would show this. So let A be the language of your first machine and B be the language of your second machine. We want to show that A and B are the same. That's what it means for two machines to be equivalent. They have the same language. We want to show that the sets A and B are the same. So then, how do we show that A and B are the exact same set? If A minus B is equal to the empty set and B minus A is equal to the empty set, then the two sets are equal.
Or if their intersection is the empty set. I mean, that's not right. Is there another way of saying that?
Yeah, your A minus B is the same thing as A intersected with B complement. So we'll go to that in a second here, but make sure this makes sense. If I have A and I get rid of everything in B, and that leaves me with nothing, then that means that B contains all of A. If you start with everything in A, and I tell you to get rid of everything in B, and you end up with nothing, that means everything in A was in B. If you start out with everything in B, and I tell you to get rid of everything in A, and you end up with nothing, that means everything in B was in A. If everything in A is in B, and everything in B is in A and B are the same set.
Do you need to state that B minus A equals the empty set?
Yes.
Yes. This is not enough for the sets to be equal. Let me show you an example. Do the set 1, 2 minus the set 1, 2, 3.
Other way around, right?
No?
I guess.
This is equal to the empty set. That does not mean the two sets are equal.
Oh.
If I start with this and I get rid of everything in this,
Oh, yes.
so then when we switch the order, it also gives us the empty set. Then they have to be equal. You see that?
Yeah.
So if A minus B is equal to the empty set and B minus A is equal to the empty set, then our two sets have to be equal. Okay, so let's note that. Okay, so now, if the machine accepting A minus B, now A minus B is the same thing as A intersect B complement. Everything in A and not in B.
Yeah, okay.
A minus B is everything in A and not in B. Everything in A and not in B. You follow that? Now, why did I rewrite A minus B like this? What do we know about intersection?
You can turn it into a union with a not.
What do we know about regular languages and intersection?
It's closed.
Regular languages are closed under intersection. And regular languages are closed under complement. So if A is a regular language, and if B is a regular language, then A intersect B complement is still a regular language. Right? So if this is a regular language, there has to be some DFA that recognizes this language.
Okay.
So if the machine accepting this regular language has a minimum of just one state, then A minus B have to equal the empty set.
Why?
This is the minimum machine that accepts nothing. Always and forever.
Okay. It accepts nothing,
Yeah, it doesn't have an accept state, and it's only one state.
so it doesn't accept anything.
So it accepts
Oh,
nothing. Its language is the empty string, or the empty set. right?
Yeah.
Okay. So that's how we can check that A minus B is the empty set. Look at the machine that accepts it and see if its minimum looks like this. So that's how we check these two things. So then if A minus B is the empty set and B minus A is the empty set, then the answer is yes, those machines are logically equivalent. Otherwise the answer is no, they're not logically equivalent. And so there's a way that we can always answer the question. For any two machines you give me, it turns out we can always determine yes or no, do they recognize the exact same strings?
Is there
When we get to Turing machines, sorry, you can't do it. Impossible. Can't answer that question in general. There's no formula like this we can come up with.
when we proved all NFAs are DFAs, we kind of made a formula you could say for taking an NFA and turning it into a DFA. Is there a second way to do that for finding the unique minimum?
Yes, there's a very procedural way of doing it.
Okay.
It just would have taken like
A long time.
a lecture in and of itself, maybe 2 lectures to go over it. So it's a huge tangent for not a huge payoff.
Got it.
It's something that teachers care about if they're going to have you like actually write an algorithm to do it. But since we're not doing any coding in this class, it's not worth the tangent. Anyways, third thing, can we determine if a language is infinite? So I give you some machine, can you determine whether or not that machine accepts an infinite number of strings?
Maybe 2 or 3.
What would you look for?
A loop.
You'd look for a loop. That's one way to look for it.
So you check if
Almost.
it's pumping Lemma?
This machine has a loop.
Loop on the way to the substate.
A loop on the way to the accept state, right?
Okay.
That's still kind of a bit vague, kind of hard to determine it. Is there a systematic way we could determine it?
You could check its regular expression.
Check its regular expression. We talked about how to convert it to a regular expression, a systematic way of doing that. If the regular expression has a star, it's infinite.
Yeah.
If it doesn't have a star, it's not. So convert it to a regular expression, check for a star. Make sense? And then, one more thing, can we determine if the language of one machine is a subset of the language of another machine? So I've got these 2 machines, can I check if the language of this machine, if machine A accepts all the strings that machine B does? Maybe B accepts more than A, but can I check if B at least accepts everything that A accepts?
It's basically, but it's kind of, I mean, it's like doing the first half of checking if they're equivalent, right?
Yeah, it's like doing the first step of checking if they're equivalent. What do we check?
See if B accepts everything A accepts, but not the other way around.
We check if A minus B is empty.
Yeah.
And we do that the same way we did up here. Make sense? So, that's it. That's the end of all the stuff we'll be talking about in chapter 1. So we just finished this circle right here, finite state machines and all their logically equivalent things. So now we'll be moving to this circle here, which is context-free grammars. And it's logically equivalent things. So we'll now be going up a level starting chapter 2. I think so. Yeah, chapter 2, because we started chapter 0.
It's only been like, what, 7 weeks? 6 weeks?
Yeah, it's been a bit. Yeah, we're definitely going through this at a much slower rate than you would in a regular college course, but that's okay because you're not regular college students. And you haven't done all the prereqs to this. Like discrete math, some of you have. Anyways, okay, so now starting chapter 2. Completely new concept, we're starting now context-free grammars. Example of context-free grammar, before we get into the exact definition of context-free grammar. Here's a grammar. We have our rules right here. A can go to 0, A1, or it can go to B. B can go to the hash symbol. What are some examples of some strings that this thing generates? We can start with A. We can replace that with 0, A1, 0, 0, A11, 0, 0, 0, A111. Replace the A now with a B. Using that one, replace the B with the hash, and we're done. It generates a string.
Is the hash just a symbol?
Yeah, the hash is just a symbol. If it's not a capital letter, it's a terminal. Always and forever, my capital letters will be variables. Everything else will be terminals.
So it's part of the alphabet?
Yes. So hash is part of the alphabet.
Are we, I feel like I've already asked this, but are we ever going to get to where we talk about the definition of a grammar? Just a grammar?
just different types of grammars.
Just different types of grammars.
Yeah. We'll talk about a context-free grammar, one that doesn't care about the context, and then we'll talk about context-sensitive grammar. And then your grammars can be divided up into your context-free ones or your context-sensitive ones.
So grammar is
So,
either a context-free or context-sensitive.
It turns out our right linear grammar here is a subset of your context-free grammars.
Okay.
So we'll just have context-free, context-sensitive. Any grammar you generate will be one of those two. Okay. So here we had our list of using our production rules, the ways that we're used to drawing this out. Another way that we could have represented the same thing is with what we're going to call a parse tree, which is what we have right here. We started with the A, and I replaced the A with an A and a 0 and a 1. And then I took that A and I replaced that A with an A and a 0 and a 1. And I took that A and I replaced it with a B, a 0, and a 1. And I took that B and I replaced it with a hash. And it's crucial to get used to these parse trees.
They're called parse strings.
Parse tree. Parse. Can't think of a sentence where you normally use a parse. And then tree, like you find in the forest. Parse tree.
Okay.
Parse adjacent.
Alright, so this is what we call a parse tree. For those of you who have some discrete math, the important thing to know from this is it's a tree, it's a graph, where all the leaves are terminal symbols and everything else is variables.
Okay.
But we'll get more comfortable with parse trees as we go. But it's very useful to represent, rather than representing our generation of our strings this way, it's very useful to use parse trees. And we'll see more why as we get more comfortable with this, but wanted to give you an introduction to a parse tree. And really quick, here's our grammar. What's the language of our grammar?
0, 1, and hashtag.
What's the language? What's the set of all strings that can be generated with this grammar?
It's basically
0
not
n,
a hash.
hashtag 1n.
0 to the n, hash 1 to the n, for any n in the naturals, right? Because we can have 0 in just a hash. We can have A just goes to B, goes to the hash, so the hash by itself is acceptable. So there's the language of that grammar. Okay, now why are these things called grammars? Let's do an example of why these things are called grammars and how these things were initially being studied. They were initially being studied more like what we'll see here in example 2, an actual grammar. More like a snippet of the English grammar, but let's look at the snippet. So we start out with, now remember when we put things between these angle brackets here, it means treat the whole thing as though it's one symbol. Right? So this is going to mean one variable. And you'll understand the terminals. Here's our terminals. Anyways, so you can take a sentence. Well, let's read through these ones really quick. We're going to be talking about sentences, noun phrases, verb phrases, prepositional phrases, complex nouns, complex verbs, articles, nouns, verbs, prepositions. Now, because I don't want to keep writing those out, I'm now going to use S for sentence, MP for noun phrase, VP for verb phrase, PP for prepositional phrase, etc. And I think you'll be able to infer what each thing is. So a sentence can be replaced with a noun phrase followed by a verb phrase. Right? Your subject and your predicate. Okay. Your noun phrase can be either a complex noun or a complex noun followed by a prepositional phrase. Your verb phrase can be a complex verb or it can be a complex verb followed by a prepositional phrase. Prepositional phrase is a preposition with some complex noun. The complex noun is an article with a noun. The complex verb is either a verb or a verb followed by a noun phrase. And then our articles, the only articles we're going to be using are a and the. The only nouns we'll be using are boy, girl, flower. The only verbs we'll be using are touches, likes, sees. And the only preposition we'll use is with. And using this grammar, here's an example of a couple strings in our language we could have generated, which it's meant to generate sentences from this. a boy sees is one that we could have done. We could have done the boy sees a flower. We could have done a girl with a flower likes the boy. Now let's just do one ourselves. So we'll start with the sentence. You'll infer from context what I mean. I'll just use capital letters without brackets now, and I think you'll get it. So a sentence, we have to replace it with
Noun phrase.
a noun phrase and then a verb phrase. So since those are next to each other, I'll put brackets there. Noun phrase followed by a verb phrase. Okay, which one should we replace first? Our noun phrase or our verb phrase?
Noun phrase.
All right, our noun phrase. Should we do a complex noun or a complex noun with a prepositional phrase?
Complex with preposition.
So we can have a complex noun with a prepositional phrase with a verb phrase, right? Okay, now let's replace our complex noun. Our complex noun has to have an article in the noun. So we have an article. For the ones that are just single capital letters, I won't bother with brackets. So we have an article followed by a noun, followed by a prepositional phrase, followed by a verb phrase, right?
Okay.
So let's pick our article. Let's not pick our article yet. Let's leave those till the very end, since those are going to be full words, and I don't want to write full words yet. So our article, that will ultimately be a full word, so we'll leave it. A noun, that will ultimately be a full word, so we'll leave it. Our prepositional phrase now, let's replace that. That has to be replaced with a preposition and a complex noun, right? So a, and a preposition, and then a complex noun.
Or just an article now.
Well, we'll keep it one step at a time, and then a verb phrase. So now, he's noting that complex noun is an article in the noun. So now we replace our complex noun with an article in the noun. So we have article, noun, preposition, article, noun, verb phrase. Now our verb phrase, should we do a complex verb or a complex verb and prepositional phrase?
Complex and preposition.
Complex and preposition. He wants to keep on going. A-N-P-A-N. And then you said, sorry,
Complex and preposition.
Complex verb and preposition phrase.
we're doing this. Complex verb, and prepositional phrase. Sorry, I know you can't say that, but I can. So now we need to replace our complex verb. Our complex verb is back where we just were.
Not down.
Oh,
Down one.
sorry. Complex verb is just a verb or a verb and a
Noun phrase.
noun phrase. Which one should we do?
The verb and noun phrase.
The verb and noun phrase. All right, so we have A, N, P,
All lines first.
A, N. We're just needing a verb. So verb for our complex verb. So with our complex verb, we just did a verb. For our prepositional phrase, let's plug that in, rather than writing out another one. Prepositional phrase is going to be a preposition
Complex noun.
and a complex noun. Our complex noun is an article and a noun. Okay, so we'll write the sentence over here. Give me an article. Give me a noun.
Flower.
Give me a preposition.
With.
Give me an article.
A.
Give me a noun.
Power.
Give me a verb.
Touches.
Give me a preposition.
With.
Give me an article.
The.
Give me a noun. Took too long. Right. The flower with the flower touches with the girl.
There you go.
Okay. So there's an example. And so people who were studying languages were studying grammars more like this, not really stuff like this. And there was a connection that we'll see next time, that these grammars are a lot like, well, if we take these grammars and we simplify it to exactly what we're talking about, it's more like these grammars, and we're going to say that they're logically equivalent to another type of machine that we'll eventually get to called a push-down finite automaton.
Push
So,
down.
Push-down. Yeah, as a stack that you push stuff on. We'll get there. Okay, so there's an example of the way that they were actually studying these grammars when these grammars were being studied. Stuff more like this.
That's cool.
Yeah, it's weird that something so unrelated suddenly came to also be talking about the same thing as machines that were being studied in another area.
Is this something we're going to deal with a lot, or is this just a cool connection you're showing us?
No, that's been the case with all these things so far. So when you talk about a right linear grammar, that happened to be logically equivalent to a DFA. It wasn't designed that way, it was discovered to be that way. And that happens to be the case. We're kind of working at this from the simplest model to the most complex models. Really, they started out studying the most complex models and worked down to simpler models. But there were people all working with the question of, what is computation? Maybe we can just have this conversation briefly. So if you go back before Alan Turing, and you were to talk to someone about a computer, and you ask him, do you have a computer? That's kind of like asking them, do you have an accountant? A computer is a person who computes. That's what they do. So during war, you needed people to actually carry out computations for calculating things like trajectory for artillery. And those of you who've taken physics, you know it might seem simple when I talk about throwing this thing through the air, but when we just talk about a little bit of air resistance, how much harder does the problem get? It gets a lot harder when you just bring into air resistance. And so you can imagine that they're trying to calculate the trajectory of artillery under certain weather conditions, everything that they're talking about. And so these were very tedious, complex computations. And so a computer typically was a woman during the war who would do these computations. The men were out fighting, you'd have rooms full of women just manually making all these calculations. And so a lot of those calculations, it would be like 20 hours worth of work to get a single calculation. And that's what a computer was prior to this point. And so when Alan Turing writes his paper, he talks about what is it that a computer, a person making computations, is actually doing. And can we talk about that exact process? What exactly is computation? What do we mean by the word computation or algorithm? We're going to say just follow the algorithm, just follow the procedure, follow these set of steps, just do this computation. What exactly is that? What are we getting at? And so that's the question that Alan Turing and others were trying to answer. And so some people were coming at this question of what is computation in different ways, and it turned out that their different ways of coming at the question were logically equivalent. So Alan Turing said, look over here with my Turing machines. He didn't call them Turing machines, but we now call them Turing machines. With what later became called Turing machines, he says, I'm able to capture what we mean by the word computation. And another man by the name of, just forgot his first name. His last name's Church. Alonzo Church? Does that sound right?
I think so.
It's almost right.
Look it up, I guess.
Either way, yeah. He came out with what we call lambda calculus. Has nothing to do with actual calculus, just a name for something. And he came with computation. It turns out that there are two different ways of coming at computation were logically equivalent. And then there's something called context-free grammars. Context-free grammars, which are getting at the same thing. And it turns out that they're also logically equivalent to Turing machines. And so these different ways that people were coming at this problem turns out to be logically equivalent ways of talking about computation.
So why are they in different circles if they're logically equivalent?
No, those are all in this circle. Lambda calculus, Turing machines, and context-sensitive grammars. Did I say context-free?
Yes.
I meant context-sensitive, sorry. Context-sensitive grammars are all up at this level.
Okay.
And so this level was the first level really developed. And then these sub-classifications came later, and there's much more sub-classifications than that in these upper classifications. Because it turns out people kept asking questions like, does this machine accept this string, yes or no? And it turns out that answers to questions like that were undecidable. Not questions that straightforward, but there's questions like in mathematics that we wanted yes or no questions to, and it turns out the answer to the question was, bad question. We can't answer the question yes or no.
Right.
And so that's when this field started to be developed. So it was this level that was being done first, and so if we were doing it chronologically, we're kind of doing this backwards. Because then they started working their way up how you could limit machines to make them do less and make them fundamentally do less. And what they really need to do this extra bit here. Because it turns out to get a Turing machine, it really is not that complicated of a device. I take a finite state machine, I give it 2 stacks of memory, and we now have a Turing machine. I give it 1 stack, it makes it way more powerful than what I can do. I give it 1 more stack, it makes it way more powerful than what I can do. I give it another stack, doesn't change anything. I give a billion more stacks after that. Doesn't change anything.
Really?
Really. So there's something about these levels, something fundamentally changing between these levels, and then we can't get past this level. No matter how much more powerful we try to make that machine, any random thing we come up with to compute,
Meaning we haven't done it, or meaning it's literally impossible?
it's not provably impossible. We
It's-
have no proof that you can't come up with something more powerful. It's just that anything you think of, chances are there's been a proof done to show, no, that's logically equivalent to a Turing machine. You know, logically equivalent to a Turing machine, one of the coolest proofs we'll do in this class, talk about it now because it's just so cool, is a 2-stack counter, which means, fundamentally, if I gave you an infinite number of rocks that you can stack, and you are only allowed to make 2 stacks with the rocks, so you can stack the rocks up on right here, and stack the rocks up right here, and move the rocks from one stack to another stack, just stacking rocks. You can perform any computation that any computer on Earth could do. It would take you a long time to do it, moving all those rocks around. But I could give you some procedure for moving those rocks around that would ultimately make you get the same answer as any machine on planet Earth doing that problem. There isn't any problem some supercomputer, some super quantum computer could solve that you could solve by just moving those rocks around. And in theory, I should be able to give you the procedure for just keep moving the rocks like this, and you'll get the answer. It's crazy.
You need a lot of time.
Huh?
You would need a lot of time.
A lot of time, but the point is you could do it.
Yeah.
And so to get enough stuff to start doing computation, you really don't need that much stuff to start. And it turns out we can't really give you anything to make you be able to do more than that basic computation. We don't know how to make it more powerful. It's very robust. Trying to make a Turing machine any more powerful. We can't come up with ways to do it. And then we can't hardly tell you anything about Turing machines. All these types of questions that you want to answer about Turing machines, turns out you can't answer them. And we'll prove that there isn't a non-trivial question you can ask about Turing machines and have it give you a yes or no answer. Trivial meaning it's true of all Turing machines.
Really?
Yeah, so if you don't ask a question that's automatically true of all Turing machines or automatically true of no Turing machines, if you ask a question that's only true of some Turing machines, then we will prove that it is an undecidable question. You cannot, in general, answer yes or no about that. And to give you a real-world example of where this comes through, will my program crash if I run it? There's no general code, there's no general formula for determining if that will happen.
No. Seeing it will happen.
Right. So,
It's kind of Alonzo Church.
what?
Alonzo Church.
Alonzo.
That's
Not,
what you said.
did I?
Yeah.
You did that?
I think I said an A. I knew it was an A, but I don't know if I said Alonzo.
You said it
Well,
was.
that's what you said.
I did?
Yeah.
It sounded right when someone else said it, but when I said Alonzo Church,
It sounded
it
better.
seemed like I was saying it wrong. All right, Alonzo Church. Anyways, we'll finish the whiteboard here and then be done for today.
We're under definition, I think.
We're on our definition. Okay, context-free grammar. So we're used to write linear grammar, so context-free grammar, not throwing you for much of a loop here. What's a context-free grammar? Same for tuple, your variables, your terminals, your set of rules, and your start variable. That's your set of variables, your terminals. Your terminals and variables can't overlap. Something cannot be both a terminal and a variable. Now, R is a set of rules where each of the rules just has to be of the form. Your left-hand side has to just be a variable. I can't have two variables over here. Your right-hand side can be whatever you want, variables or terminals, but your left-hand side has to just be a variable.
Why is that?
That's what means to be context-free. Your replacement of it doesn't depend on its context in the string. Let me give you an example of a context-sensitive grammar really quick. So I might have S goes to AB, or it goes to BA, and then I might have AB goes to 0, 0, A, and I might have BA, well maybe I'll also do BB here. I don't know, I might end up making a mess of things. But the point is, when you have multiple on it, I can't just replace an A with something, I need an A and a B next to each other to replace it with something.
It has to have context.
And so it depends on the context of where the variable shows up, which is why it's called context sensitive. And yeah, try just throwing one out without thinking, because it might become more confusing. But yeah, so that's why we don't have, that's why it's called context free versus context sensitive. So context free, the context for replacing the variable doesn't matter. And finally, s is a start variable. So here's an example of grammar, now written out exactly. So the grammar G4 is equal to, here's my set of variables, we just have s. Here's my terminals, a and b. My set of rules r we'll give out later, the same way we give our delta function later. S is our start variable, where r is these rules. S goes to ASB, or SS, or the empty string.
What does SS look like?
Okay, let's generate a string here.
So you treat-
So I'll start with S, and I can have S goes to ASB. I can have that goes to ASSB, replacing now my S with SS. And then, I don't know, replace that S with an AB, so now I have AA, SB, SB,
Yeah.
right? Now maybe I want to replace that S, so then we get AA, SB, ASB. And now maybe I want to replace both those with epsilons now, and so when it's all said and done, we have AAB, AB.
So it's that makes sense. It's exactly what it is.
No, I'm missing a B somewhere. I screwed something up.
There should be another B on the end.
There should be an A before you.
That's correct.
S.
Here we went S, we did SS. Now I replace this S with an,
No, when you replace the far right S on the top line,
let's see, here to here, I replace this S, right?
Yeah.
it's from your right to your bottom left.
You did AS, it should be ASBB.
AS,
Oh, right.
BA, I see, BB.
Yeah.
Good, and then that puts a B there, okay.
Or the
Because we should have the same number of A's and B's. Huh?
Oh, why makes that parse tree pretty handy. You can track your work. The parse tree, you made?
Yeah. Parse trees are also handy, that's not relevant for this, never mind.
They're all series.
Well, the way where the place parse trees are super useful is when you're writing a compiler, then you essentially, when you're determining how to replace code, you construct these parse trees. So we'll give you an example of something like that right here. So if we were to write a compiler that can do basic arithmetic, here's a type of grammar that we would need. That is nothing. That's something we did before. Okay, so let's look at another grammar here. Grammar 5, our set of variables is ETF. That stands for expression, term, and factor. Our terminals are A. We're going to think about A as just being any number, plus, times, left parenthesis, right parenthesis. Our set of rules, we'll give it a second. And our start string is E, which is an expression. So this is the grammar for generating some mathematical expression that just has plus and times in it. With me so far? And so our rules are going to be, you can replace an expression with an expression plus a term, or just a term. You can replace a term with a term times a factor, or just a factor. And you can replace a factor with some expression in parentheses, or some number A. You with me? Okay, so we're going to generate these two strings now. So let's generate A plus A times A. And we're going to generate with a parse string generation. So we start with our expression. Now I'm trying to generate A plus A times A. What am I going to replace my expression with?
E plus T.
E plus T. So we're going to replace that with E, T, and then we'll ultimately have a plus down here. So maybe we can write it all out when it's all said and done. So, and a plus, right?
Why isn't it one thing? Oh, never mind.
Then you're gonna have E goes to E plus T and T goes to T times.
I may have, so this E goes to what?
The E stays there.
The
T
E goes to E plus T.
This E goes to E plus T?
I think so.
No.
We already have our plus there.
Yeah.
So change the T to T times that.
So this one's just going to go to T.
Yes, sorry.
Wait, why?
Yes.
That could go to E plus T too.
Because T is going to go to A.
We can't do another plus. We already have one plus generated.
Okay.
And we can't.
You with me?
Where's that in the rules? Like, you only have one plus. We only need one plus.
We only need one plus. So now we have a T, we have a plus. We're always looking at the leaves of this thing for our string so far. So far our string is T plus T. And you're always looking at the bottom, the leaves, the bottom. You with me? So our string so far is T plus T. Now we need to replace our right T with ultimately an A times A, and we need to replace this T with an A.
We're supposed to generate something.
Oh yeah, we're generating this exact string. Sorry. Okay. Yeah, that makes sense. So this T is ultimately going to be replaced with an A, right?
It's going to go to F and then A, right?
Oh, sorry, did we skip a step? This is going to go to F, and then it's going to go to A. This T over here is going to go to T times F, right? So this goes to T times F. This T is going to go to an F, and then an A. And then this F is just going to go to an A, right? And now that we have all these written out, I could have done what we did before and done a long arrow down, plus, and a long arrow down, times, and make that a longer arrow. A. Now when you're looking at a parse tree, the terms that come together first are the ones that get evaluated first. So looking up the tree, we would have done this A times A before we did the plus. So imagine that we were now working backwards. So if you saw in code, if you saw on a screen, A plus A times A, you ultimately, if you're the one writing the compiler, need that to ultimately all come back to just one number.
Yeah.
And so you would be like reverse engineering this. And so notice that these two terms come together before this term and this term come together with the plus. And so it's going to cause the times to happen before the plus happens. And so it's preserving precedence.
Okay.
It's not going to add these two A's before it multiplies these two A's together.
I'm missing what you're saying.
Ultimately, when this gets computed by a compiler, it needs to compute A plus A times A.
Right.
So imagine that this one had the number 3 plus 2 times 1. We don't want to do 3 plus 2 is 5 times 1.
Right.
In this case, it worked out either way, huh? Let's put 3 there. Okay. We don't want to do 3 plus 2, which is 5, times 3 is 15.
Right.
We want to do 2 times 3 is 6, plus 3 is 9. So notice that our parse tree brings these two A's. If you look at the parse tree backwards, going up the tree now, it brings the A's together into a single term before it pluses with this A. When does this A get plus to this? Looking backwards up the tree, those get brought together up here. And so this parse tree happens to be preserving precedence. And so if we were to try and break precedence with our parse tree, and try to force it to do the A plus A first, then the way we set this grammar, it's going to force there to be parentheses around it. And so our grammar happens to preserve that. We chose this grammar intelligently. And so this is going to be a good grammar. We'll see a naive attempt at a similar grammar here in a sec, which isn't as nice. Okay, so expression, now we're generating this one. So what am I going to generate first?
T, E plus T.
I'm going to do,
Just T.
yeah, let's
You
do
want to get it to
up
the
some.
parentheses.
E goes down to just T, T goes to
T times F.
T times F,
Oh,
right? Now, this T right here, we're going to replace with a F,
Which it becomes an E.
which is then going to become an E in parentheses.
Right.
T can't become P. F does.
Yeah, F does.
Oh, T turns.
T became F, F became E with parentheses.
Yeah.
Now this E, once again,
Turns into E plus T.
turns into a plus, a E,
Becomes E plus A.
and a T, right? And then this E turns to T, turns to an F,
Turns to A.
turns to A, E, T, F, A. This T turns to F, A. We did that, now we still gotta do this F. This F turns to A. And so now, let's extend our arrows here. So extend this arrow all the way down. That was our left parenthesis. Extend this arrow all the way down. That was our plus. Extend this arrow all the way down. That was our A. Extend this arrow all the way down. That was our right parenthesis. Extend this arrow all the way down. That was our times, and extend this arrow all the way down. That was our A. And so here's a type of grammar that you might have to use in a compiler if you were trying to do, you want your programming language, which you would want it to be able to do basic arithmetic type stuff. Yeah, it is cool. A lot of fun building compilers. So now let's look at one that's kind of similar, but a bit more naive of a grammar. And it's going to have a terrible, terrible problem in it that we don't like for our grammars. It's going to be what we call an ambiguous grammar. So this one we're just going to deal with expressions now. And it's just going to be able to throw pluses in there and times in there, however we want, willy-nilly. And so now we're going to generate this string again. And now we're going to see that there's two different ways of generating this string. So now I can take this expression E, and I can have it start by going to E plus A, E plus E, I mean. Another way I could have done it is I could have had this E, and I could have started it with generating an E times E. And then I can take this E over here and replace it with an E times E, right? So I could replace this one with a E times E. And I could replace this E over here with an E plus E. E plus E. And then finally replace all my E's with A's.
Doesn't that go to the residence?
Well, notice that one of them says do your times first, then your plus. This one said do your plus first, then your times. And notice that they generate identical strings. They both generate A plus A times A. If we replace all our E's with A's now, right?
Okay.
So, if you have two different parse trees that generate the exact same string, we call that grammar ambiguous. So this grammar is what we call an ambiguous grammar.
So generally, you only want one parse tree.
Yeah, when you're doing something like coding, you want it to be one and only parse tree. And so we don't just use any context-free grammar when we're doing coding, not coding, compilers. When you're building a compiler, you don't just use any type of context-free language that you want. You use a special type of context-free language. We call them LRK grammars. LR, and then you see it like that, K. K is some variable. It could be 0, 1, 2, 3. Unfortunately, we won't have much to say about those, but I don't know why I said it.
Well, it makes, I mean, it's good. It helps me.
But anyways,
Context.
so this grammar up here was not an ambiguous grammar. There was only one way to generate the string, and there was only one way to generate the string. This grammar right here is ambiguous. We found two different ways for generating the exact same string. Make sense? So that's what we mean by ambiguous in general. So here's our definition now. A string W is derived ambiguously if there exist two or more unique parse trees for W. For deriving W, I probably should have said. Then a grammar is said to be ambiguous if it generates any string ambiguously. So if there's any string you can generate in an ambiguous way, we call the grammar ambiguous. Make sense? Intuitively, with languages like the English language, grammar being ambiguous, you can ultimately tell from statements like this. The boy saw the girl with the mirror.
Right.
So you get statements like this where you can't really interpret where to put the mirror. Is with the mirror. Is the mirror what the boy saw the girl with, or was the girl holding a mirror when the boy saw the girl? You understand the ambiguity there? The boy saw the girl with the mirror, so I'm the boy. Do I see a girl holding a mirror, or do I have a mirror and I'm looking in the mirror to see the girl? The boy saw the girl with the mirror. And so there's an English version of sentence being generated ambiguously. So the English grammar is an ambiguous grammar. There would be two different ways of generating the string ultimately using the English grammar. One that associates if we built the parse tree, the with the mirror would either be how the boy saw, or the with the mirror would be describing the girl. And we'd either see the with the mirror come with the girl, or we'd see it come up with what the boy saw if we built a parse tree for it. Kind of captured in precedent. Where does it combine it? One more example of grammar, and then we'll be done. So let's come up with a grammar now that generates an equal number of zeros and ones. An equal number of zeros and ones. A context-free grammar.
Is there a way to prove this, that a grammar is ambiguous or not?
Is there a way to... So, I'm 90% sure, but I could be wrong here. In general, for a context-free grammar, asking, is that grammar ambiguous, is an undecidable question. And there is not a general formula for determining whether or not a grammar is ambiguous.
But we basically can assume that...
You can determine it for a particular grammar. This undecidable stuff, it can sometimes get confusing between we don't have a general formula versus we can't figure it out at all. Those are two different things, so let me give you an example.
Like a brute force effect. You can prove it through brute force, but you can't really prove it.
Not through brute force. So I'll give you an example. You know, if I had an equation like this, ax squared plus bx plus c equals 0, no matter what a, b, and c I choose there, you could figure out a solution to this equation with the Pythagorean theorem, or not the Pythagorean theorem, the quadratic formula. You know that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So if your problem looks like this, this will give you the answer. And there's a formula to do it. And if instead I would have given you something like this, ax cubed bx squared plus cx plus d equals 0, then there's also a similar formula. It's massive. It's not a nice simple one-liner like that one. It's a massive formula, but there is one. And if I would have given you ax to the 4 plus bx cubed plus cx squared plus d plus e equals 0, there's still a formula. Did I do it wrong?
ds.
Oh, thank you. dx plus e equals 0. There's still a formula, and it would take up all these boards to write out the formula. But there is one. Now, if I do a fifth power polynomial, there is no longer a formula. Provably, there is no formula. Now, we're not smart enough to think of one. I can prove that there isn't one. Not I can, but people can. There is a proof that there isn't one. Now, that doesn't mean that we can't solve particular ones. So in general, we cannot solve things that look like this. ax to the 5 plus bx to the 4 plus cx to the 3 plus dx squared plus ex plus f equals 0. There is no general formula for solving those. But if I give you the particular problem, x to the 5 equals 1, okay, x equals 1 is the solution. So I can give you problems where you're able to think of the solution, but there is no general formula that you could always and forever use, the way that you can use a quadratic formula for quadratic equations. That's what we mean by these things are undecidable. When we say a problem is undecidable, it doesn't mean that you can't come up with solutions to particular problems. It means that in general, there is no solution.
So just take case by case.
Yeah, so you can look at a case, and you can probably figure out in the case.
So you could prove that that's the top one there is definitely not ambiguous.
Right, so I think for context-free grammars in general, asking is it ambiguous is undecidable, but there is a subset of these grammars, which are LRK grammars, which it isn't undecidable anymore. So it's only when you try to calculate the formula for all of them that it no longer works. Okay. And maybe we'll pick up with an example next time to re-wet our feet. So we'll call it there. Any more questions? All right. See you guys next week. Sorry about the long break.